Okay, welcome back to a new week. So we're going to finish up these slides today about qualifiers and quantifiers. I guess we're on to the quantifiers bit. Remember those with the upside down A and sideways E for all and there exists? So this is how we can mathematically specify things that happen a lot, all the time, or sometimes. Okay? So now we're ready to come like full circle because I'm teaching you this, I guess at the end of the day, to like become better programmers, right? So I want to show you how to go from like English statements of something that you want to mathematical expressions that precisely tell you or express what you want, and then finally to code that goes and finds that thing that you wanted at the very beginning. Okay, so that's the kind of three-step process that you always kind of have to do in your mind when you're programming. Okay, and so I'm going to try and teach that to you. So the first thing that I want to say is just introduce some terminology. There's this thing called a predicate, which I've kind of glossed over when I talked about quantifiers. Deep down, there really was a predicate in these examples. Okay, a predicate is just a proposition, so something that is true or false, right? Something. That's what a proposition is. That can be evaluated to true or false. A predicate is just a proposition with some variables in it. And I think you remember we had a ton of variables like in our quantified statements with for alls and there exists. So like a predicate would look something like this. It's kind of like a function, p of x. You can define that to be, I don't know, let's see here, x has a cat. Okay, and this would be a predicate because just saying this by itself, x has a cat, it doesn't tell you, it doesn't give you back true or false. It's almost a proposition. It has a variable in it, which means if you were to replace x with something real, like Lawton, for example, then it would become true or false. And so p of Lawton is true. Okay, that's the idea. So a predicate is just a proposition with some variables in it, and we could take the things that we talked about last time and like translate them into predicates, saying like for all x's, for all people, p of x is true, which is like everyone has a cat. Okay, that's what that would translate to. So hopefully you can see how this might help us, because this is very similar to like plugging in values in a function, and that can help us write code. Okay, so it's all coming back, coming around. Let's do this. So we're going to practice some more saying what we're thinking precisely. Okay, that is the translating English to math part. And then once we're there, it's pretty self-explanatory to get from math to code once you know a few tricks. Okay, so here's the first thing that we want to do. We would like to find a prime number that is greater than 50. Okay, so just think about that. We can call this x, and we need to ask ourselves, what is true about x? Like, what does this mean, really? Okay, so let's try and make this closer to math. And so let me move down the window. Okay, so this is the same statement converted a little bit to math. Okay, it's like x is greater than 50 and x is prime, a nice little logical combinator. You know our and. So that looks a whole lot more like math. This is what's true about this x. Okay, so this could be a predicate. You give me an x, and I'll tell you whether or not this is true or false. Okay, like 51, for example. Yes, it's greater than 50, but it's not prime because it's divisible by 3, right? Because 5 and 1 add to be 6, and that's that little trick. So this could be translated further to this, which is using little tiny predicates inside. So this could be itself a predicate, asking if something is prime. See that? It's predicates all the way down. So that's the idea. So this is even more mathy, like pretend we have a predicate that will tell us true or false whether or not something is prime, and then we can check if this number is greater than 50 as well. And I think I need a new mouse because it keeps clicking for me. Okay, so the idea is if we can find some x for which this is true, what can we say? Okay, if we can find some x for which this is true, what does that mean? Hint, hint, using quantifiers. Okay? What does that mean? Think about it, pause the video, take a good guess, and then let me show you the answer. If you can find some x for which this is true, okay? Maybe I should say that. If you can find some x such that the above is true, let's bring all this back inside, then the following statement is true, this one right here. There exists an x, which means that I don't know which one, but there is one, such that the rest of this is true. So that x, that particular x that you're telling me about, it's greater than 50 and it's prime. Okay? So this itself could be a predicate, and this like makes it a proposition again that can be true or false. Okay? So every quantifier, that's a nice key idea that we should remember. Every quantifier, it introduces a brand new variable, because it's like, okay, there is something called x, and this is true about it. Okay? This part over here is true about that x. Okay? So this is saying we can find at least one x greater than 50 that's prime. Okay? And that is a true statement. Okay? I think you should imagine that there is, or I think it's easy to imagine that, yes, there's a prime somewhere greater than 50. Somewhere, at least. Okay? So this is a true statement. Slash proposition. Because remember, propositions are things that can be true or false. In almost proposition, like this side right here, that's just a predicate. You need to give it an x. But once you quantify over that x, then it's suddenly something that can be true or false again. Okay? That is the idea. That's how you prove that, if that makes any sense at all. So here's what we want to do. We're still trying to do this. We want to find a prime number that's greater than 50. And now we have a nice mathematical statement that tells us what we want. Okay? So we can write a program to do this. Okay? I encourage you to pause the video and think about like what the strategy would be to find some x that for which this is true, okay? For which it's greater than 50 and it's prime. What would be your strategy? Okay, how would you program this? So take a quick second to think about that, and maybe assume like you have an isPrime function that will tell you if like it's true or not. Okay, like isPrime of 42 will give back false, for example, in Python. So assume you have this. If you could use isPrime, what could you do to discover a prime number that's greater than 50? Okay, so depending on your strategy, here's one. There are plenty more. Okay, here's the one that I came up with. All right, so you can iterate through all the numbers. So you just go and you like use your range-based for loop. You'd be like for I in range, blah blah blah. You start at 51. So you get to start at 51, see if it's prime. Okay, if it's not, look at 52, see if it's prime. Look at 53, see if that's prime. Yeah? On and on and on until you find a prime number. Who knows where it is? Maybe it's 53. I can't remember. Okay? So, yeah, just try all the numbers starting at 51. Call the first one I, or the current one I. So this is like, it's just a variable. Okay? So I gets to start at 51, and then it can have a chance being 52 if 51 wasn't prime, and then if 52 wasn't prime, we can give it a chance at being 53, on and on and on until we find a prime. If I is prime, stop. Okay? If it's prime, we stop, and then we say, oh, yes, we're good here. Okay? That is the idea. That is the idea. Okay, so let's see here. I think, yeah, now it's time to implement this. Okay? The next one's just another example. So let's go to idle and make a new program. Right? We're going to finally come full circle and translate that English statement up here that we translated to math. We're going to translate this now to code. Okay, this is pseudocode, so it's not really Python yet, but we're going to use it to program what we want. Okay, so let's give this a name before I forget. And this is code from class, CSCI 1, and this should be lecture 22 then. Let's go with that. Here we go. And we can say it's like, I don't know, primes.py or something. How about that? So here's what we want to do. We want to iterate through all the numbers starting at 51. Okay, so we can say I is 51, I is starting at 51. First number to try is 51, and then we're going to keep going while it's not prime, right? So if I is prime, we want to stop, so we can say while I is not prime, right? So let's pretend we have an is prime. That will give us back true or false, telling us that the number is prime, while I is not prime, okay? So remember that not like takes a truth value and it negates it, we say. Oops, there goes my mouse that doesn't work again. If you say not true, that becomes false. If you say not false, that becomes true. And you, of course, can combine this with other things, like is it not true that 42 is less than 43? False, yeah. That is the idea, okay? So it just takes something logical and negates it. That is not. And so we want to continue. We want to keep searching while I is not prime. You see how I'm reading that? While I is not prime, okay? And the not is key here. So while I is not prime, keep looking. I equals I plus 1. Keep looking with the next I. And so I hope you see what's going to happen. I starts out being 51, and we're going to keep on checking, hey, is I prime yet? Is I prime yet? Is I prime yet? And if it's not, we're going to keep on incrementing I, 1 by 1 by 1, okay? Maybe it becomes 52, then it becomes 53 while it's not currently prime yet. And then the second it is prime, right? Maybe I is 53 and 53 is prime. Let's pretend it is at least. Then this is going to become true. You see that? So this whole thing now, not is prime, becomes false, and that will stop the loop, because loops only continue while the condition is true. And so once I is finally prime, the condition will become false. So when I finally becomes prime, the loop will stop because not is prime I will become false. Okay? And that stops the loop. We don't continue loops when the condition is false. Okay? So that is, that's it. We can just say which one we found. Shout out the number we found. So, I don't know, print the first number, the first prime number greater than 50 is, drum roll please, and then we can give I. Okay? So that is going to be our program. I hope you see how it works. And that is how that's going to work. So we're going to keep on searching for prime numbers, and we're going to stop once we find one and print it out. Now the last piece of the puzzle is prime. We need to find out whether or not a number is prime, and we need to make this function, okay? So this will return true if n is prime, okay? And the secret to testing for primality is this. We check for remainders, okay? So a number is prime. I'll write this over here. Like n, a number n is prime when all the numbers, when from like 2 to 3 all the way to n minus 1, don't divide into n, okay? Don't divide cleanly into n. That means it has no factors, okay? Like you can't divide anything by it and get a 0 remainder, okay? So for example, the remainder operator, by the way, is the percent sign. So 42 divided by 2, what's the remainder? You say 42% sign 2. I say mod 2, okay? So this is going to be 0 because when you divide by 2, you have nothing left over. But when you divide 41 by 2, you have 1 left over. That's the remainder, okay? So we can check if the remainders are 0, and that'll tell us if n was prime, okay? So for, I don't know, for x in range 2 to n, because that'll go to n minus 1, right? So try all the numbers from 2 to n minus 1 and see if they divide cleanly into n. if x divides, because x will get a chance being all those numbers, divides cleanly into n, then this number was not prime. Then n is not prime. So, for example, we found that 2 divided cleanly into 42, so obviously, obviously 42 is not prime. It has a factor, at least one, it's 2, okay? See how we're doing that? So we can say, if, now here's the fun part, we try to divide n by x and get the remainder. If that happens to be 0, that means x divided cleanly into n, okay? And in that case, we need to give back false, because that immediately tells us that n is not prime, okay? That is how we say that, okay? So that's our if statement, and so we want to try all the x's, give them a chance, being 2, 3, all the way to n minus 1, see if they all don't divide into n, and if they all don't, we'll be done. This loop will stop, and we'll be down here, okay? If we got here, then nobody divided into n. That means n was prime. And we can return true, okay? You see that? So that is how you write is prime. Technically, you don't have to go all the way to n minus 1. You could go up to the square root of n, but that is a example for another class, okay? So this is a nice, easy way to find out if a number n is prime. We'll give back true or false, whether or not it was. And now I think we have everything we need to find the first prime number greater than 50. Are you ready? Okay. Oh man, it looks like 53 was prime. Isn't that fun? So that is how we went from what we want to code after an intermediate step, figure out exactly mathematically what we need, because this looks a lot like code. It's like if x is greater than 50 and it's prime, that's very close to being code. You see that? It was quite easy to translate it to pseudocode and then to Python. That is the hope, okay? So isn't that fun? And you can find the next prime numbers, like, okay, we didn't like 53, so let's start at 54. Okay, let's just do that for a second. Rerun it. And apparently, 55, 57 weren't primes, but 59 was. Okay, that's how you can find them. So I'll set this back to 51, and wasn't that fun? So the fact that our program gave us back the answer, like gave us back 53, kind of tells us that we proved this statement true. Do you see that? That's really interesting. There is a correspondence between programs and proofs that is a topic of a much later computer science class, but at least I'm hinting at it to you now. Programs can be proofs. I hope you see that now. We used the program that we just wrote to find a prime number that's greater than 50 to prove that this statement right here is a true statement. Okay? So that's fun, and hopefully that was exciting. So that's my first example. Now I have another one. Okay? So let's prove that for all numbers n between 0 and 100, for all, hint hint, for all those numbers, the square root of n is less than or equal to 10. Okay? And I think that's a true statement, right? Because the second it gets to 10, it's at 100, right? It can't get any bigger than that because of the way the square root function works. It doesn't jump around. It goes and slowly gets bigger, right? So it becomes 10 only when it gets to 100. Okay? So let's try that. Let's try all numbers, all the integer numbers between, let's say ints, that are between 0 and 100, that the square root of n is less than or equal to 10. Okay, so the first job is to convert this to English that looks like math, okay, kind of how we did this right here. Can you give that a try yourself? Maybe pause the video. That is a very good thing to know how to do, okay? So here is what I came up with. If n is greater than or equal to 0, and n is less than or equal to 100, that will cover all our bases, like we try all of them, between 0 and greater than, and 100 and less than. So that translates to this. So if that's true, then the square root of n is less than or equal to 10. Okay? So do you remember how to translate ands to logic? And do you remember how to translate if-thens to logic? Okay, that is important. So let's go and do that, okay? Because we need to convert this to real math with symbols, right? If and then can be replaced, and can be replaced. Are you ready? Give it a try yourself, of course. Here's what that would become, okay? So remember that if then becomes implication right there, okay? It like packages if then together. This is the if side, this is the then side. So if it's true that n is greater than 0 and it's less than or equal to 100, then the square root of n is less than or equal to 10. Okay? That is the key. Okay, so this is a predicate right now, because it's still got an n sticking out of it, and it's not true or false because it depends on that n. Okay, so it's a predicate. It's like a function in logic. Isn't that fun? So then we need to create a proposition, okay? How do we do it? Well, we want to prove that all the integers between 0 and 100. This is true. So, which one are you going to add? Yes. You will add for all n. For all n, it's true that if n is between 0 and 100, then the square root of n is less than or equal to 10, and that is a proposition. That can be true or false, that we can prove. And one way to prove it is with code. Okay? So, yeah, here is, if you were wondering, and you forget when I say it, here's how you translate, for posterity, this code, or sorry, not this code, this mathematical code, I guess, to English. All right, so it's saying for all n, and we're going to imagine that n is an integer only. If n is greater than 0 and n is less than 100, then, okay, oops, less than or equal to 100, then the square root of n is less than or equal to 10. Okay, that's how you can translate that to English. And now our job is to prove or disprove this statement. Okay, we think it's true, but can you write a program that confirms that thought? Okay, that's the key. So how would you prove that for all numbers n that are between 0 and 100, this is true? No? How would you do it? Okay, so here's my idea. All right, we want to try all these numbers, right? So we need to iterate again. We got a loop. Loop is key. So we want to loop and try like I starting at 0, at 1, at 2, all the way to 100, and give them all a chance, okay? Give them all a chance to fail, okay? That's the strategy. Because we can try to take the square root of all of them, right? We can try and take the square root of 2. We can try and take the square root of 1, and the square root of 100. And see if any of them, see if there are any of them that are equal, not equal, that are strictly greater than 10, okay? If that's true, then this is false. You see that? That is one way to discover whether or not they all were true, okay? Because we kind of want to do, hey, is it true for 1, and is it true for 2, and is it true for 100? And one easy way to do that is take the flip side of it and find the first one where it's false. And if it is, we're done. Otherwise, if we get through the whole loop without ever complaining, that means that they all worked. You see that? It's like reverse psychology, reverse questioning. So then we print true if that happens. Okay, that is our way of proving or disproving this statement that is probably better in math. Okay, we can prove or disprove that with this code. You see that? So we just try all the numbers and see if the square root is what we think it is. Okay, that is how you can translate this and prove it using code. Okay, so let's try to make a new program. What should I call this program? Prove that for all numbers n. I don't know. How about square root? I can call it square root. Square root underscore proof or something. How about that? So I need to use the square root, which means I need to import the math library, because math gives me the math.squareRoot function that I could call and figure out the square root of any number. Okay, so now we can do the proof. Okay, so we're going to loop through all the numbers between 0 and 100 and see if the square root ever messes up. Okay, so how do you loop through every number between 0 and 100? Well, 4 is a good one, or a while. For I, we could use I in range, so 0 and 100. So you can say range 0, 101, yeah? Or because it starts at 0, you can also just use range of 101, okay? Those are the same. So we're going to try every number. Every number, call it I, between 0 and 100, and then we're going to check, okay? If the square root of, not n, but I, is greater than 10, then it's false, okay? Or we can say maybe, like, what's the best way to do this? Yeah, I think we can say is true for our statement. Okay, is true is something. Okay, let's guess that yes, our statement is true from the very beginning. Okay, let's guess that our theorem, we say, is true. The thing that we're trying to prove, we can call it our theorem, and let's see if we find a counterexample. And that'll turn it false, right? So if the square root is greater than 10, then it's not true anymore, okay? We didn't prove our theorem. So is true equals false now, okay? And if we got through without ever finding a counterexample, then the theorem was true. Is true will still be true because we didn't find a way to make it false. And then we can just use that to print out whether or not our statement was true. Okay, so we can say, one thing that we can do is we can totally still print true and false with an exclamation point, but it gets a little weird because we say print is underscore true, and then a comma, and then a single quotation with an exclamation point. What this is going to do is, well, it is a true statement, so we can say, let's run it. It's like true, but then there's like a space between that. One thing that you can do to fix that is to say a string. Make a string out of the Boolean value, the true or false value. So convert it to a string, and then add at the very end of that an exclamation point, and that'll fix it. Yay, so now it says true. So we proved our theorem. Do you understand how this is a proof? It's like, okay, let's pretend that it's true, see if we can find a way to make it false and disprove it. But if we got through this whole thing without ever disproving it, it was true, this never got changed, and we'll print out whether or not we found a counterexample, whether or not it was true. Okay, so that is how we can prove that statement, true or false. Isn't that beautiful? And we can also make false statements, like for all numbers between 0 and 101, it's not the case that this is all true, right? Because that'll be greater than 10. So if I make this 102 for a second to go between 0 and 101, it's always one less. We found a counterexample, no! So again, this is a way to prove things. A program is really a way to prove things. Isn't that fun? So that is, yeah, that's really what I wanted to talk about. So let me continue, and we're going to end early a bit today because you have a longer than usual essay to work on, and then a new one assigned. So you're welcome. So yeah, I guess the moral of this story is that logic and computer science, they are better together, joined. So use logic when you're trying to think about what to do, how to make your program correct, okay? Because you want to always write correct programs as soon as possible. I know we all make mistakes when we're programming, but the use of logic under the hood, like we were doing, makes it a lot easier to write a correct program, okay? I think you can hopefully see that from these examples. And it also helps you like find counterexamples, argue why existing programs that I don't know why this doesn't work. Well, if you think through it logically and try and figure out maybe some proofs about your programs, then it becomes easier to figure out whether or not it's wrong, or if it is definitely wrong and it's not returning the right answer, to understand why it's wrong. Okay, so yeah, give logic a try. Hopefully I am just slowly brainwashing you to use logic in the back of your mind as you're programming. So that is my idea. So let me go pull up your next essay, and then we'll end early and give you some time to work on your current essay. Okay? All right, so for your next essay, the one after the 1,000-word one, is a very philosophical one. Okay, so I'm going to make you, I'm going to force you to have an opinion on art. Okay, so what I want you to do is pick your favorite painting. If you don't have one, go and find one. Okay, and pick one that was made sometime before 1900. So it's got to be like 1899 and previous. All right, so back before there was any amount of technology and electricity wasn't that common. Okay, so like Renaissance, Impressionists, whatever you're interested in, or if you want to find a new interest, go for it. Okay, so it's got to be made before then, and then I want you to imagine that the artist was alive today. Okay, and that artist made the same painting on a computer. Okay, so they were using like Photoshop or Affinity, whatever, and they had a drawing tablet instead of a brush. Okay, or I guess it was a virtual brush, right? So would that painting still seem as beautiful to you? Okay, so I want you to think about that long and hard. Would the painting that was made virtually this time by the same artist, would it be just as beautiful? Okay, so obviously that is in the eye of the beholder, in the eye of the essay writer, and that is exactly why I'm asking you to write this essay. Okay, so why or why not analyze and explain what you're thinking? Okay, so this is a 750-word essay. Just go ahead and respond to this prompt, and yeah, I want you to cite at least one work, and I found a few nice sources about this kind of topic, and I think that there's also a little bit in your book about it. So digital art is a very fun world. If you have not seen it, here are some people that are like on opposite ends of the realism spectrum that I follow on Instagram. So take a look at them if you're like wondering about like what people can do with digital art and how it looks. Yeah, that's all I want. So cite one thing, 750 words, about your favorite like pre the digital age artwork. Okay, so that is all I have for you. Good luck. Yell at me if you have any questions, and I will see you in the programming lecture.